section 5.1, approximating area under the curves. So we're gonna look at the major part of it. The first one, actually the first one, we're gonna look at the approximating area by the Riemann sum. The Riemann sum is just the name of the typical sum to approximate the area under the curve. And then the second part is area under a curve, which is the function, the velocity function. So that is kind of the application of the approximating area by the Riemann sum. Okay, the the technique that we're gonna use is some textbook they use the term slice and sum. Slice and sum. Think about the name slice and sum. So you're gonna have the function to begin with, which is the curve. When you draw the graph, I just draw the random curve. Okay, this is the graph of the y equals f of x. And slice and sum, that means if we have the function and we're gonna find the area or approximate the area between x equals a and x equals b. So we're gonna make a bound. So from here is a and stop at b. So our goal is to approximate the area under the curve. Slice and sum, that means we're gonna make the equal partitions, the equal subinterval. For example, we're gonna make it to have the n equal subinterval from point A to point B. To make it equal, so you have to find the total length. So then the width of the interval, we use the delta x or the change in x, which is from the difference of the b and a. That's the entire length here, b minus a, and divided by n, or the number of the subinterval that you want to have. Make it equal subinterval. So this case is called the slice step. So slice it, and then you have like in this case, we have 4 equal subintervals, and the goal is to approximate the area under the graph. Next, we're gonna sum of the area of the small rectangles under the graph. So there are 3 different ways that we're gonna cover. The first one, we use the midpoint approximation. The second case, we call the left endpoint approximation. And the last one, we call the right endpoint approximation. And the name is just tell you the process, how to get the work done. For the midpoint, for example, from point A to point B, if we break it into n equal subintervals, I'm going to name it as this is x0 and x1, x2, x3, x4. In this case, n equals 4. So that means the points from A to B, there are 5 points. So 1, 2, 3, 4, 5, and make it 4 equal subintervals. We have the left end, the right end, and 3 interior points. So the midpoints for this case, if we name this as x0, x1, x2, x3, x4, the midpoint can be the point in between x0 and x1, which can be found by x1, like you add them and then divided by 2. So x0 plus x1 divided by 2. So that would be called like x1 bar, or the average of the two values here. And then the second one gonna be x2 bar, which is x1 plus x2 divided by 2. And the next gonna be x3 bar, x4 bar. So the midpoint, you have to do some more calculation before we get to the approximation. So the points that we use for the midpoint gonna be x1 bar, x2 bar, x3 bar, and so forth. The bar, that means you find the average of the left and the right ends of each subintervals at each subinterval. And then for the left end point, for the left end point, excuse me, from the real number line, I try to give you in the virtual format. So if we have x0, x1, x2, x3, and x4, in this case n equals 4, right? For the left endpoint, we're gonna use the left end of each subinterval. For the first one, between x0 and x1, the left end is x0. And then for the second subinterval, the left end is x1. And the same. So you're gonna use the x0, x1, x2, and x3 as the point of calculation for the left endpoint. And then for the last case, for the right endpoint, with the same breaking points there, the x0, x1, x2, x3, x4. For the right endpoint, the first subinterval, the right end is x1, and the next right end x2, x3, and x4. So the points of calculation for the right endpoint approximation gonna be x1, x2, x3, and x4. How do we use the endpoints or the point of calculation? Because your goal is to find the area. Think about when you find the area, if you use the left endpoint, I use the same graph here. The left endpoint, the first one, the first bar, the first area here, I highlighted here. Okay, we use the left end, so that means for the first interval, the left end is right here. So we're gonna use the left end to calculate the height of this bar. The second one, same way, use the left end as the height of the bar, the left end as the height of the bar, the left end as the height of the bar, and then calculate the area of each bar. The area of the rectangle is the length times width, and the width is the equal width, which is the delta x. So the length, which is the height of the bar, that depends on the x that we use to calculate. So for the case of the left end point, like what I show on the screen here, this function height going to be the function at x0. Next height is going to be the function at x1. And next the function at x2, function at x3. So the area of each bar, I would use the term, I'm going to squeeze in here. So the area A1 is the width times the height, or the width times the length, which is the delta x that we calculate by using the total length divided by the number of the subintervals. The first area is the width times the height. The second area is the same, the width times another height, and so forth. And the idea of this is to sum them all up. So then the approximate of the area, or the A, approximately equals to the sum of all small areas. Okay, small areas. So the whole technique here is called slice and sum technique. And this is, I mean, the name of it is called the Riemann sum. So the sum of the areas of the rectangles here under the curve, that we make it into the equal subintervals. Okay, so this is the big picture of the concept. So I'm gonna summarize it. So the Riemann sum, that's the name of the technique, and the informal name is the slice and sum. Okay, we're gonna start with the function f of x, which is non-negative. Why is non-negative? Because the graph gonna be above the x-axis. Okay, over the interval, the cross interval AB. So you have to know point A and point B, or the left bound and the right bound of the graph. The objective of this Riemann sum is to estimate the area under the curve, or between the curve and the x-axis. Recall the function is non-negative, so the graph going to be above the x-axis. And then to estimate by what? By summing the areas of the adjacent rectangle. Okay, so that's the purpose of the Riemann sum, to approximate the area under the curve. And step one, we're going to partition the interval AB, which is a closed interval, into n subinterval. So then the width is the delta x, we use the notation delta x or the change in x. Delta x is b minus a, which is the total length, divided by the n, which is the number of the subintervals. And then the a is the beginning of the bound or the left end, and b is the end of the bound. So you're going to have a as x0 and b as the xn, and you have the interior points as x1, x2, and so forth. So for our case, the earlier example, I gave the example when n equals 4. So then the a gonna be x0, and then the interior points gonna be x1, x2, x3, and then the point b gonna be x4. Okay, the left end, the right end here. So that's a step one. You slice them. So make it into n equal subintervals. And then step two, choose one value for the x in each interval and label it C1, C2 up until Cn. So don't worry about the notation C here. The case that I gave earlier gonna be three cases. The case that we're gonna use the midpoint. Um, so it could be the midpoint. It could be the left endpoint or the right endpoint. So those are the choice that you're gonna choose for each problem. So you don't choose all of them at the same time. You're gonna pick one or the other. Okay. So step two, you choose one of them. The problem gonna indicate very clear. Use the midpoint approximation, use the left end approximation, the right approximation, and so forth. And then the next step, you find the corresponding y value. How do you find the y value? It's from the function provided at the beginning. So you know the function y equals f of x, and you know the points that you choose, either the left end, the right end, or the midpoint. Okay, I call it points of calculation. So you find the function value, and this value are the height of the rectangle. So the height of the rectangle. And then to form the area, so you multiply the height and the width, which is the function value and the delta x. Okay, after you get that, you add them all up like this. The area, see the f at c1 times delta x, that's the area 1, or the area of the first rectangle, plus the area of the second rectangle, plus all the way until the area of the nth rectangle. And since they all are from the way that we break it up into n equal subintervals. So the delta x gonna be the same value. So you can factor it all out. And basically you can approximate the area by using the product of the width and the sum of the function values. Then the function of values at all the midpoints, or the function value of all the left end of each subinterval, or all the right end of the subinterval. So the overall process here is called the process of finding the Riemann sum. Riemann sum, okay, which is the approximation of the area between the curve and the x-axis. So this slide is the summary of the concept that we're gonna go over for 5.1. Questions? Yeah. All right, look in more detail for each technique. The left, the right, the midpoint Riemann sum. For the interval, I just give you more graphs here. For the left Riemann sum, the left from the graph, let's see if I can make it bigger. As you see, if we consider the left Riemann sum, make a partition like from point A to point B into n equal subintervals. So the first one, the x subscript 0 or x naught equals a, and then x1, 2, 3, and so forth. In this example, n equals 5 because we have 5 equal subintervals. And then use the left Riemann sum. So for the first subinterval, the left end is at x0 or at x equals a. So use that point to calculate the height of the rectangle. And then the next one, the next subinterval, the left end is at x1. Use x1 as the height of this rectangle. Use the same technique. Use the left end point to calculate the height of the function for the left Riemann sum. Okay, so you're gonna have some like extra area or you are losing some area. So that's why it's called approximation because the error will occur. Um, if you have the higher number, the greater number of the n, the better approximation you're gonna get because you're gonna have less the less extra area or you are losing the less area, something like that. So for the right Riemann sum, similar idea, the same graph with the equal n, like n equals 5 subintervals. For the left n, and for the right n, the first subinterval, the right n is at x1. So use x1 to calculate the height of the bar, same as the second and the rest of the intervals. So the right end will be used to calculate the height of the rectangle. So you gain some, you lose some, depends on the function that you have. Okay, and then the other one, the last one is the midpoint Riemann sum. From point A to point x0 to x1, we are going to calculate the middle one, the middle value, which is the point between the left and the right end. You calculate it from adding x0 and x1 divided by 2 to come up with the midpoint, and then use the midpoint to calculate the height of this rectangle. So more calculation for the midpoint Riemann sum, but this is the best approximation among three different ways because it's adjusted within each process, each step of the process. Because as you see the picture here, let me clean up a little bit so you can see. Um, from the picture, you can see in one bar, you gain some, you lose some, gain some, lose some. It's adjusted within itself where when we use the left Riemann sum, either you totally gain or totally lose for each rectangle. Okay, so that's why midpoint Riemann sum is the better approximation comparing with the left Riemann sum and the right Riemann sum. So another summary page here. And let's see if I can move it over. So another summary page. The Riemann sum, it can be used the sigma notation to represent it. Okay, since we add all the area of the small rectangles, like the first rectangle, second rectangle, and so forth. And then when you rewrite it as the product of the width and the sum of the function values, the sum here, it can be written in the summation form because you have n of them, the sum of the n term. So f of the point of calculation or the height of the rectangle, you have n equals subinterval. So the sum of n term, I mean the sum of the first n terms here, each term multiplied by the delta x. So this is another way to write the Riemann sum or use the sigma notation to represent the Riemann sum.